For those wishing to gain a deeper understanding of the science that brain candy is inspired by, this is a comprehensive review of stroboscopic light stimulation and the visual hallucinations it induces. This paper, published in the journal Neuroscience of Consciousness, traces over 200 years of research from experiments in 1819 to cutting-edge neuroimaging studies revealing the brain mechanisms underlying these experiences. Links and credits will appear in this video's description. You'll learn about the geometric patterns and colors people see, the cultural history surrounding the artists and creators who have leveraged the effect, and the current scientific theories about how rhythmic light creates these profound alterations in consciousness. Whether you're curious about the neuroscience, the phenomenology, or the therapeutic potential of stroboscopic experiences, this review provides a thorough foundation for understanding the tools and techniques that inspired brain candy. Stroboscopically induced visual hallucinations, historical, phenomenological, and neurobiological perspectives. Part 1. Introduction. Commonly reported stroboscopically induced visual hallucinations mainly consist of vivid experiences of color and geometric patterns. Less frequently reported are complex hallucinations containing semantic content, as well as experiences associated with altered states of consciousness phenomena, such as out-of-body experiences, changes in time perception, and emotional responses. In addition to being fascinating in their own right, these visual hallucinations are of interest as a model for studying visual hallucinations under laboratory conditions, allowing for a systematic investigation of their phenomenology and the neural mechanisms that underlie them. Recent theoretical and neurophenomenological work has begun to elucidate the neural mechanisms underlying these experiences, potentially providing insights into properties of the visual system. Since the 1960s, stroboscopic light stimulation and the experiences it induces have occupied an obscure yet fascinating role in culture, spawning a wide variety of devices and experiences, some of which have been developed as works of art. In addition, some practitioners have sought to use these experiences as a recreational or therapeutic tool, drawing on the parallels in experience with psychedelic substances. This article summarizes the history of these visual hallucinations in science, culture, and medicine, providing a comprehensive review of their phenomenology as well as the proposed neural and psychological mechanisms that may underlie these experiences. Part 2. Stroboscopic light stimulation. Techniques and terminology. Hallucination-inducing stroboscopic light stimulation typically involves bright periodic light flashing between approximately 5 and 50 Hz, most commonly viewed through closed eyes. The eyelids serve as a medium to diffuse the light across the visual field, but this can also be achieved through other methods, such as goggles which diffuse light or bright strobing computer screens. Precise brightness thresholds for the induction of these hallucinations are difficult to establish due to a variety of factors which may influence their induction, including the level of ambient light, individual differences, and how tightly a participant closes their eyes during stimulation. However, brightness levels in the range of 1000 to 5000 lumens reaching the closed eyelids has been shown to reliably elicit these hallucinations, although they may occasionally be experienced outside of this range. For comparison, an average household LED bulb emits only around 800 lumens, while a typical smartphone flashlight emits around 50 lumens. Safety measures must be taken to mitigate the risks associated with exposure to stroboscopic light stimulation, such as for people with epilepsy or sensitivities to bright lighting. In the literature, stroboscopic light stimulation has been referred to using a range of terms such as flicker light or intermittent photic stimulation. We propose that the clearest term is stroboscopic light stimulation for its specificity in referring to light that flashes at controlled intervals, and will hereafter refer to it as SLS. Stroboscopic light stimulation most effectively induces visual hallucinations when spread evenly across the visual field, which is commonly achieved by applying it on closed eyes, although other methods using open-eye stimulation with diffusion goggles have also been applied. Some authors use the term Ganzfeld flicker or Ganz flicker to refer to open-eye stimulation, such as when using strobing computer screens. The German term Ganz refers to a uniform coverage of the whole visual field and should not be confused with Ganzfeld stimulation, a perceptual homogenization technique also termed perceptual deprivation, which can also induce hallucinations, though with a different phenomenology. Other studies using strobing stimuli on computer screens include checkerboards and annuli, which may also give rise to these hallucinations with distinct phenomenology. Stroboscopic light stimulation is also distinct from other methods that induce visual phenomena, which involve flickering stimuli, such as pattern-induced flicker colors or frequency tagging, which do not aim to induce visual hallucinations and likely involve different neural mechanisms. Few visual hallucinations are reported with SLS below 5 Hz or above flicker fusion, the latter being the frequency at which stroboscopic light becomes subjectively indistinguishable from constant light, which may be 50 Hz or higher, depending on the conditions and participant. The periodicity of SLS has been shown to be highly relevant for the induction of these hallucinations, which diminishes if flashes are presented periodically. Alterations to aspects of SLS, such as frequency, color, duty cycle, which is the percentage of each period in which the light is on, and brightness are known to affect the reported phenomenology of the experience. While these parameters are typically held constant in laboratory experiments, recreational applications of SLS often manipulate these parameters to create more dynamic and varied experiences. Visual experiences induced by stroboscopic light also have been referred to by various terms including hallucinations, phosphenies, imagery, or pseudo-hallucinations. We suggest that the most suitable term is hallucination, defined as sensory experiences that do not correspond to external stimuli, as would normally be the case for an individual's baseline waking perception. This avoids conflating these experiences with other distinct phenomena, such as mental imagery or entoptic phenomena. Pseudo-hallucinations is a term used in psychiatry to refer to hallucinations, usually pathological in nature, where the patient is aware of the non-veridical nature of their hallucinatory percept. It is rarely used in contexts where non-pathological hallucinations are purposefully induced, such as with psychedelics or SLS. We also avoid the term phosphenies. This term is usually used to refer to visual experiences in the absence of stimulation with light, which is distinct from the visual hallucinations induced by SLS. Part 3. Safety considerations for human exposure to stroboscopic light. The primary risk factor for serious adverse effects from SLS is photosensitive epilepsy, although not all individuals with epilepsy are susceptible. While photophobia is common in epilepsy, photosensitive epilepsy represents only a small subset of cases. Its prevalence in the general population is low, with an annual incidence of approximately 1 case per 100,000 people. Photosensitive epilepsy may be up to 6 times more prevalent in children and adolescents aged 7 to 19 years than in adults, leading to an estimated lifetime prevalence of about 1 in 10,000. Although epilepsy, including its photosensitive form, is heterogeneous, there is broad agreement that it has a heritable component, as it frequently occurs in multiple members of the same family. Additionally, individuals with high anxiety find certain types of bright light uncomfortable, with stroboscopic lighting in particular being anxiety-inducing. Studies have also associated autism spectrum disorder with hypersensitivity to bright light. For example, photophobia increases with autistic traits. Furthermore, commonly reported external triggers for migraines include bright, intense light, flickering light with strongly contrasting light and shade, However, it should be noted that while certain environmental stimuli are frequently reported as triggers for migraine pain, there is ongoing debate regarding how such stimuli influence the onset of migraines. Part 4. History of the use of stroboscopic light stimulation. Research investigating the phenomenology and potential neuronal mechanisms of stroboscopically induced visual hallucinations dates back over 200 years, beginning in the early 1800s with introspective reports of the phenomena. The first wave of systematic investigation began in the 1950s, branching out from research into the electrophysiological responses to stroboscopic light. Since the early 2000s, there has been a resurgence of interest in SLS, driven in part by the revival of psychedelic research. This second wave has focused on gaining a better understanding of both the phenomenology and potential neural origins of these hallucinations. Concurrently, SLS has also been utilized in cultural and therapeutic contexts since at least the 1950s. The timeline of this history shows key scientific and cultural milestones. These include Purkinje's drawings of his hallucinations, the first known documentation of the phenomena in 1819. A rendering of the 4 Kluver form constants from 1926, which are geometric forms posited to make up simple geometric visual hallucinations, consisting of checkerboards, targets, tunnels, and spirals. An early EEG experiment involving SLS at the laboratory of William Gray Walter. Such experiments eventually led to the rediscovery of these hallucinations and the first wave of research into the phenomena. Kroger and Schneider's brainwave synchronizer, an early stroboscope sold as a medical device. Gessen's Dream Machine, a hallucination-inducing stroboscope that can be constructed from household materials which he invented and which is often credited with introducing these hallucinations to culture at large. A schematic of the arrangement of the dark and light frames used by Conrad for his short experimental film, The Flicker, from 1966, created to induce hallucinatory experiences in the audience using a variety of SLS frequencies synchronized to sound. One of Gorge's mind gyms, where members of the general public could use SLS goggles for their posited therapeutic benefits. fMRI data of neural activations during these hallucinations showing a correlation between thalamocortical activity and the hallucinations. An early group strobe session with the Lucia No. 3 strobe light. Rule, Stoff-Regan, and Ermentrout's models of these hallucinations, which simulate the content using neural field equations from 2011. Collective Act's Dream Machine, an experience which used stroboscopic lighting combined with music to induce hallucinations for tens of thousands of people within a collective setting, with many attendees reporting experiences reminiscent of altered states of consciousness. To our knowledge, the first description of stroboscopically induced visual hallucinations was published by Purkinje in 1819. He described an introspective experiment where he induced these hallucinations by looking towards a candle flame and waving his hands in front of his closed eyes, and documented the geometric patterns he observed. He discussed these observations alongside other subjective phenomena, such as mechanical and electrical phosphonies, in which visual experiences are induced by pressing on the eyes or electrically stimulating visual nerves, and speculated on the physiological origin of these phenomena. Soon after, the Scottish scientist David Brewster published his own exploration of these hallucinations, including the first published observations on how they may vary with frequency. For more than a century after Purkinje's original publications, no influential studies on these hallucinations were conducted. There were only occasional mentions in relation to other phenomena involving flashing light, such as pattern-induced flicker colors, until the advent of EEG reawakened interest in the topic. Part 5. First Wave Stroboscopic Light Stimulation Research, 1900 to 2000. While early scientific discussions of various types of hallucinations primarily involved qualitative introspection, By the 20th century, researchers began collecting qualitative reports of visual experiences from groups of participants and synthesizing the results to develop theories on the origin and perceptual contents of visual hallucinations. In 1926, Heinrich Klüver published his influential manuscript Mescal Visions, an eidetic vision, in which he proposed a classification system for geometric visual hallucinations induced by mescaline, identifying four-form constants. This classification system was later suggested to make up the majority of all reports of simple visual hallucinations across differing pathologies and induction methods, including stroboscopically induced hallucinations. In the mid-1900s, the advent of EEG sparked interest in stroboscopic light as a useful scientific tool for modulating EEG activity. Through this research, these hallucinations were rediscovered by chance, which quickly led to a series of illuminating studies on the corresponding subjective effects of SLEs. Most notably, William Gray Walter conducted pioneering studies after rediscovering the phenomena during his research. In contrast to contemporary research into these hallucinations, this period was marked by experiments with smaller sample sizes, more emphasis on qualitative research, and a wider variety of stroboscopic induction techniques. Riemohl conducted a series of small experiments investigating how the luminance threshold for the perception of these hallucinations changed with frequency, color of the light, and monocular versus binocular SLS. Smithies conducted a series of experiments aimed at describing and classifying the contents of these hallucinations. He categorized the types of patterns and movement participants reported, noting the high intersubject variability in subjective reports. He classified the geometric patterns into categories including unformed elements, rectilinear patterns, radial patterns, curvilinear patterns, and formed images or complex hallucinations. Smithy's thorough description and classification of the phenomena did not gain much traction in the scientific community. Instead, Klüver's form constants became the dominant classification system used in modern studies despite many reports containing geometric formations that extend beyond Klüver's classification system. The history of stroboscopically induced visual hallucinations intermingles with much of the history of psychedelic research and mirrors the rise and subsequent suppression of psychedelic research in the 1900s, in that interest peaked in the 1960s but gradually waned over time. However, since the turn of the century, there has been a second wave of interest in these hallucinations, both culturally and within communities researching hallucinations, psychedelics, altered states of consciousness, and related phenomena. Part 6. Second Wave Stroboscopic Light Stimulation Research 2000 to present. The post-2000 second wave of strobe research was characterized by more controlled, quantitative experiments, investigations into stroboscopically induced altered state of consciousness, phenomena, neurophenomenology, and the use of these hallucinations as a model to study simple visual hallucinations in other contexts. Large-scale quantitative phenomenological research has used stroboscopic frequency as an independent variable and has begun to elucidate more systematically how these hallucinations may be affected by stroboscopic frequency. Recent decades have also seen advances in the neurophenomenology of these hallucinations, which aims to capture first-person descriptions of phenomena of interest, such as visual hallucinations that are amenable to neurocognitive methodologies, including experiments linking phenomenological measures with brain imaging data from functional magnetic resonance imaging and EEG. MRI research has found thalamocortical activity to be implicated in the induction of these hallucinations. Other studies have used EEG to investigate the electrophysiological correlates. A decrease in lower alpha band activity, 8 to 10 Hz, has been observed to correlate with increased frequency of hallucination reports. Shevelev and colleagues found that different hallucinatory geometric forms were reported by participants when the SLS was synchronized to an individual's peak intrinsic alpha frequency. Comparing these hallucinations to psychedelic experiences, some experiments have examined whether the electrophysiological correlates of SLS-induced experiences resemble those associated with psychedelic experiences. While exposure to SLS has been found to correlate with increased neural signal diversity and other electrophysiological measures associated with psychedelic states, similar changes in EEG signals have also been observed at frequencies which do not induce visual hallucinations, a common control condition in experiments. This suggests that the observed EEG effects may reflect the influence of the SLS itself, rather than being specific to the presence of visual hallucinations. Another avenue of research has used these hallucinations as a model of visual hallucinations in various contexts. These hallucinations have been hypothesized to share broadly similar neural mechanisms with other types of simple visual hallucinations, and they can be much more easily induced and controlled in the laboratory with healthy participant populations compared to hallucinations arising from other etiologies. Such experiments have used these hallucinations as a tool to investigate the occurrence of visual hallucinations in Charles Bonnet syndrome, psychosis, and Parkinson's disease. Researchers have also used strobing stimuli on computer monitors to research these hallucinations online and augmented with other visual stimuli. Pearson and colleagues used a strobing ring on a computer screen to induce a simplified model hallucination, finding that the content of the hallucinations induced by this stimulus displayed properties of multi-stability, as well as replicating the frequency-dependent findings of other research. Part 7. Cultural and recreational use of stroboscopic light stimulation. While it is unknown when humans first began to experiment with these hallucinations, the phenomenon entered into the cultural consciousness throughout the mid-1900s. This was largely due to the independent rediscoveries of the phenomena by William Gray Walter and the Beat Generation artist Brian Gysin. While much was elucidated during the first wave of research about its basic phenomenology and potential neural mechanisms, this work rarely left the confines of laboratories. In contrast, Gysin developed the Dream Machine, a stroboscope that could be constructed using household materials. This device would soon find its way into the homes of artists and bohemians throughout the 1970s and the 1980s, as well as in art exhibitions around the world. Gysin's was perhaps most significant for the influence he and his Dream Machine had on other artists, including musicians Kurt Cobain of Nirvana, Brian Jones of the Rolling Stones, and Paul McCartney of the Beatles, as well as other Beat Generation writers like Allen Ginsberg and William Burroughs, Gysin's closest collaborator, and the artist Keith Haring. Influenced by both scientific and creative explorations of these hallucinations during this period, structuralist filmmaker Tony Conrad experimented with using film projectors to induce hallucinatory experiences. His 1966 film, The Flicker, may have been the first artistic work to vary the frequency and duty cycle of stroboscopic light over time in synchrony with music and sound in an attempt to produce a more structured and engaging hallucinatory experience. This notable innovation in the artistic use of SLS not only inspired a niche movement of experimental flicker films, but also prefigures the contemporary cultural resurgence of interest in strobe, which often uses sequences of synchronized SLS and sound. Mirroring the two waves of interest in scientific research in SLS, artistic work surrounding these hallucinations waned in the late 1900s before experiencing a resurgence of interest beginning in the 2000s. Gysin's Dream Machine in particular has seen a renaissance of new art and commentary, inducing the publication of books, projects inspired by Gysin's work, and these hallucinations, a documentary film, and recreations of Gysin's Dream Machine available for purchase. In the early 2000s, Procol and Winkler developed digitally controlled stroboscopes with adjustable frequency, duty cycle, and halogen wash lights, allowing for the creation and proliferation of stroboscopic sequences synchronized with music, marketed as the Lucia No. 3. This approach influenced the design of subsequent devices and platforms for curated SLS experiences. In 2021, the Luminate mobile phone app was launched, utilizing the inbuilt flashlight LEDs on a smartphone as a strobe in combination with music and guided meditations, reaching over 1 million users globally. In 2022, the UK-based art installation Dream Machine, inspired by Gissin's original concept, used SLS and music in a curated setting to explore group experiences, introducing tens of thousands of attendees to these hallucinations. Through the past 2 decades, hallucination-inducing stroboscopic light sequences have become a distinct art form, using the parameters of the strobe light itself alongside music, environment, and framing to create curated hallucinatory experiences. Part 8. Rumors of ancient stroboscopically induced visual hallucinations. The existence of these hallucinations in ancient cultures is plausible, but evidence is lacking. Gissin stated that Nostradamus would wave his hands in front of his eyes while staring at the sun to induce these hallucinations, but no other sources have been found that support this story. Schumacher discussed the potential of fire-gazing as a source of ancient hallucinations, but these claims lack concrete anthropological evidence. Some sources have stated that the ancient Greek philosophers Ptolemy and Apuleius observed these hallucinations induced by light shining through the spokes of a spinning wheel. However, the original Greek texts appear to only discuss other optical phenomena involving spinning wheels, such as motion-induced color mixing, with no clear reference to these hallucinations. It remains plausible that these hallucinations may have existed in ancient cultures, given the importance of altered states of consciousness and visual hallucinations in many cultures, including the ancient Greeks, and the ease with which these hallucinations can be independently discovered. Several publications discuss apparent rediscoveries of these hallucinations where the authors were unaware of the phenomena before encountering it. Part 9. Medical and therapeutic applications of stroboscopic light stimulation. Alongside decades of reports of altered state of consciousness experiences among the cultural use of SLS, some researchers and practitioners have argued that the experiences induced may have medical or therapeutic benefits. Despite this long history of research and practice, these claims remain controversial. Besides SLS, other periodic stimulation methods, including repetitive transcranial magnetic stimulation and rhythmic sound, have been widely investigated by the medical community for their neurophysiological effects and therapeutic potential for disorders such as epilepsy, Parkinson's disease, and depression. However, bright SLS is unique in the phenomenology it induces, which may, in turn, produce positive experiences that mediate therapeutic benefits. Indeed, within the field of psychedelic-assisted therapy, it has been argued that the acute psychedelic experience itself may be pivotal for therapeutic outcomes, as opposed to such outcomes being purely pharmacological in origin. It is unknown, however, if SLS-induced experiences share any mechanisms with psychedelic-altered states of consciousness, or merely have suggestive phenomenological similarities. Research-backed medical benefits of SLS-induced experiences remain elusive. One of the earliest medical applications of SLS-induced experiences occurred in 1959, when physician Dr. William S. Kroger and inventor Sidney A. Schneider introduced the brainwave synchronizer. This device was marketed as a tool for inducing hypnotic states in order to reduce pain during surgery, positioning it as an alternative to anesthesia. However, the pain-reducing effects of the device were later attributed to participants' expectations. Pain relief only occurred when researchers informed participants that they should expect this effect, suggesting that the observed reduction in pain was not driven by SLS itself. This finding, coupled with the device inducing seizures in several patients, led to a sharp decrease in its popularity during the 1960s. Since then, Other researchers have continued to investigate the potential pain-reducing properties of SLS, although none have successfully isolated this effect from participants' expectancies. Indeed, the potential influence of participant expectations, or more generally, demand characteristics, remains a challenge for SLS research today. In 1982, psychiatrist Dennis Gorgeous patented the brainwave synchro-energizer, a set of goggles designed to induce SLS experiences, spawning a wave of practitioners who used such devices for their purported medical benefits, such as stress reduction and cognitive enhancement. Over the following decades, many similar devices were developed and sold, leading to the establishment of hundreds of mind gyms worldwide, which provided SLS experiences to the general public. Researchers investigated the potential medical and well-being application of these devices for anxiety, phobias, depression, and memory, among other conditions. Results were mixed and often limited by flawed methodologies. The lack of robust evidence supporting the potential medical applications of these devices, combined with concerns over their potential to induce seizures, has led to controversy, including legal action against one manufacturer. Although these devices never gained widespread medical acceptance, they continue to be used by some practitioners and members of the public for medical and well-being purposes to this day. It remains unclear to what extent the phenomenological experiences induced by SLS may contribute to the treatment of a range of mental health conditions. In psychotherapeutic contexts, SLS has been used in a manner similar to, or in combination with, psychedelic-assisted therapy. Although this specific approach remains under-researched, proponents of the practice argue it can bring about therapeutic benefits in a manner similar to psychedelic-assisted therapy through the mechanism of acute altered state of consciousness experiences. Recent research has reported promising response rates for psychedelic-assisted psychotherapy in controlled settings with screened participants, though not all such research has yielded positive results. Some studies further suggest that the acute psychedelic-induced visual experiences might mediate the long-term improvements in mental health rather than being solely a result of pharmacological action. Initial reports from psychotherapists have also found that SLS combined with psychedelics may induce more complex visual hallucinations, potentially intensifying the experience. Psychotherapists have also noted that the use of SLS in the context of psychedelic-assisted therapy has the further advantage of being easier to terminate than psychedelics, as these hallucinations are rapidly extinguished when the light is turned off. The combination of SLS with psychedelics may also allow for a reduction in the dosage of psychedelic substances used in this context. It is important to note concerns about the safety and efficacy of psychedelic-assisted therapy, which may both undermine the motivation for SLS therapy if acute altered state of consciousness experiences turn out to be not so impactful, or increase this motivation by ameliorating safety concerns specific to psychedelics. A small group of psychotherapists have been using SLS for the above purposes since the first wave of research. Psychotherapist Stanislav Grof tested SLS alongside psychedelics while developing protocols for psychedelic-assisted therapy and as an alternative following the prohibition of psychedelic substances. Other practitioners and therapists have continued to explore the psychotherapeutic potential of compassionate use of SLS for various psychopathologies. These therapeutic approaches partly overlap with both historical and contemporary concepts in psychedelics-assisted psychotherapy, particularly the idea that psychedelic-induced altered states of consciousness can serve as transformative experiences. Finally, reports of SLS use within trauma therapy, specifically eye movement desensitization and reprocessing, exist. An additional application currently being explored is the use of SLS as a preparatory tool for psychedelic-assisted therapy. This approach offers the possibility to familiarize the patient with the therapeutic procedures and experience of altered states of consciousness, where SLS allows a fast termination of the experience in case of feelings of discomfort or adverse reactions. In this context, SLS serves to reduce concerns about the ability to cope with a challenging psychedelic experience and to train the patient to open up and let go when altered state of consciousness experiences start to emerge. Stroboscopic light stimulation has been started to be used in a clinical setting as a preparatory step before ketamine-assisted therapy, although no systematic research on this subject has been published yet. Rigorous research is needed to test the potential effects of SLS in a controlled manner, accounting for factors such as demand characteristics, expectancies, and the placebo effect. Part 10. Phenomenology of experiences induced by stroboscopic light stimulation. Although the perceptual content of SLS-induced experiences was initially studied through introspection and qualitative measures, recent research has aimed to quantify these hallucinations and altered states of consciousness. This shift seeks to develop a more precise understanding of the phenomenology of these experiences and how they may be influenced by factors such as strobe frequency or inter-individual differences in personality. Contemporary qualitative methods that have been applied to these hallucinations include interviews, textual responses, and drawings, while quantitative measures primarily rely on questionnaires developed in the context of psychedelic research, which assess altered state of consciousness-related experiences or tasks developed for the context of a given experiment. Some experiments have also incorporated psychophysics-like tasks to obtain more fine-grained perceptual data on specific perceptual qualities of these hallucinations. The most universal aspect of the phenomenology of SLS-induced experiences is that of simple visual hallucinations, mostly consisting of geometric formations, a phenomenon readily replicable under laboratory conditions. Visual depictions of such hallucinations exist from the early 1800s to the present day. Complex visual hallucinations and other phenomena associated with altered states of consciousness, including alterations to bodily perception, time perception, and emotions, are also reported, though this is more common in cultural SLS contexts and is not always replicated under laboratory conditions. Visual depictions of geometric hallucinations include Purkinje's early drawings of his hallucinations induced by waving his hands in front of his closed eyes while observing a candle flame. This appears to be the first published drawing of these hallucinations, and more than a century would pass before any new drawings would be published. Participant drawings from later research studies also exist, showing various geometric patterns and forms. Part 11. Phenomenology of simple geometric visual hallucinations. The majority of research investigating SLS visual phenomenology has focused on the prominent geometric aspects of these experiences. The most widely used classification system and theoretical frameworks for the geometric formations within simple visual hallucinations is Kluver's form constants and the rotationally symmetric Turing patterns generated by neural field model simulations of simple visual hallucinations. However, research investigating the phenomenology of stroboscopic experiences consistently shows that participants report a broader variety of geometric forms than these frameworks can accommodate. For example, neural field models posit that all simple visual hallucinations should be organized around the center of the visual field, where the highest level of detail occurs. In contrast, phenomenological studies reveal a mix of rotationally and translationally symmetric forms, such as grids and lattices. Furthermore, these hallucinations also appear to exist on a spectrum between regularly organized geometric formations, for example checkerboard, and non-geometric phenomena, such as visual noise, with many hallucinations being reported as falling somewhere between these two extremes. The current models and classification systems for simple visual hallucinations therefore fail to account for the range of hallucinations reported in phenomenological research, with a wider variety of geometric forms, visual noise, color, and dynamics likely composing their phenomenological content. These hallucinations appear to change in content based on the frequency of stimulation. For example, Smithies found that doubling the SLS frequency mid-stimulation subjectively doubled the spatial frequency of the hallucinatory geometric pattern. However, this relationship has not been systematically explored, partly due to the lack of an effective measure for the spatial frequency of hallucinatory content. The phenomenology of hallucination geometry may be linked to the alpha frequency band, 8 to 12 Hz, within the brain. Numerous studies have found that geometric visual experiences peak around the alpha frequency range. When the stroboscopic stimulation frequency was matched to participants' individual intrinsic alpha frequency, Shevelev and colleagues found that participants were more likely to report radial patterns at intrinsic alpha frequency compared to 1 Hz above or below intrinsic alpha frequency. Another prominent aspect of the visual phenomenology of these hallucinations is color, with many individuals reporting color as one of the most salient features of the experience. However, interpreting data on the specific colors experienced during these hallucinations are challenging. The most common method of inducing these hallucinations involves participants viewing the stroboscopic light through closed eyelids. Neutral or warm hues can be perceived when light passes through the eyelids due to the properties of blood and skin. Research investigating stroboscopically induced color experiences using this method of stimulation has shown that lower stroboscopic stimulation frequencies, below alpha, tend to result in reports of neutral or warm colors, while frequencies at or above the alpha frequency range, 8 to 12 Hz, are more likely to induce cooler colors such as blue, green, and purple. The reported blues, greens, and purples are unlikely to be entoptic and therefore more likely to be cortical in origin, while the warm and neutral colors experienced at lower frequencies may correspond to entoptic colors seen with constant light behind closed eyes, resulting from light passing through the eyelids. Surprisingly little has been reported about the temporal dynamics of these hallucinations, how hallucinatory content evolves and moves over time, despite these dynamic features being a common and salient aspect of reported experiences. Motion oriented around the center of the visual field appears to dominate stroboscopic experiences, with participants frequently reporting rotational or spiral motion as well as zooming in or out. Chaotic motion with no apparent pattern is also reported, along with more intricate transformations such as one geometric pattern morphing into another. Similar to reports of geometric formations, the perception of movement in these hallucinations has also been reported to peak around the alpha frequency range. In experiments using a strobing annulus, Pearson and colleagues found that increasing the strobe frequency resulted in faster perceived hallucinatory movement. Part 12. Phenomenology of complex visual hallucinations and altered states of consciousness. Outside of simple visual hallucinations, which dominate reports of SLS-induced phenomenology in laboratory experiments, a variety of more heterogeneous experiences are reported, primarily in cultural contexts, which include other altered state of consciousness phenomena such as complex visual hallucinations, out-of-body experiences, and emotional changes. It remains debated if SLS indeed directly induces altered state of consciousness phenomena outside of simple visual hallucinations, or if instead these phenomenologies have a distinct mechanism, potentially top-down in nature or otherwise expectation-based, which may not be directly linked to the SLS itself. While simple visual hallucinations consist primarily of colors, textures, and geometric formations, which are most likely correlated with lower-order areas of the visual system, complex visual hallucinations contain more semantic content with likely neural correlates in higher-order cortical areas. In the context of SLS, complex visual hallucinations are generally reported as being shorter in duration and combined with the more common simple visual hallucinations, such as a semantic object briefly appearing among the abstract hallucinated geometries. In cultural contexts, however, complex visual hallucinations that are more immersive, dramatic, and narrative in content have indeed been reported. Complex visual hallucinations also appear less affected by frequency than simple hallucinations, including reports of complex visual hallucinations coming from experimental conditions consisting of SLS flashing outside the frequency range known to induce simple geometric visual hallucinations, such as 3 Hz. This lends some credence to the idea of complex SLS phenomena having a distinct mechanism. It is also difficult to disentangle complex visual hallucinations from pareidolia. Naive hallucinators may describe or interpret simple visual hallucinations in semantic terms, such as by describing visual noise as clouds or checkerboard patterns as brick walls. Beyond hallucinations, a variety of other altered state of consciousness phenomena have been reported during SLS, particularly outside of the laboratory. However, the occurrence of altered state of consciousness phenomena during SLS is by no means a universal experience. Commonly, studies find that there is little or no altered state of consciousness phenomena other than these hallucinations experienced, or that only a portion of the tested population experience altered state of consciousness phenomena. Such reported altered state of consciousness phenomena include out-of-body experiences, emotional changes, euphoria, or changes to temporal perception. As music or sound is often present during SLS, experiences of audio-visual synesthesia or interactions between the visual and auditory experiences are sometimes reported. Stroboscopic light stimulation experiences have been described as somewhat resembling psychedelics-induced experiences without drugs, and as a potentially transformative therapeutic experience. The nature of SLS-induced altered states of consciousness have been described as dreamlike states or hypnagogia and hypnotic states. Several factors may explain the discrepancy between the near-universal reports of simple geometric hallucinations and less frequent reports of other altered state of consciousness phenomena in laboratory settings. In cultural contexts, SLS often involves variations in frequency, duty cycle, ambient light, and light colors, which combine to create a more dynamic experience. Furthermore, these events typically pair SLS with music, which may enhance the emotional impact of the experience. Together, these elements may contribute to the increased reports of altered states of consciousness at such cultural events, though no study has yet tested if such elements may induce altered states of consciousness where static strobe frequencies do not. Other factors may contribute to experiences and reports of altered state of consciousness phenomena. Firstly, demand characteristics giving rise to implicit or explicit participant expectations may lead participants to report having altered states of consciousness in contexts where they implicitly or explicitly believe they are supposed to experience them. Relatedly, specific psychological traits may contribute to the occurrence of altered states of consciousness in SLS, such as phenomenological control, which refers to an individual's ability to alter what they experience, both within and outside of the hypnotic context, in ways that are consistent with their plans and goals. In cultural stroboscopic events, participants' expectations, shaped by advertising and the setting, may influence the nature of their experiences, including complex visual hallucinations and altered states of consciousness. Few studies have tested the contribution of phenomenological control, psychological, or environmental factors on reports of stroboscopically induced altered states of consciousness. Recent studies indicate that participants who have higher absorption scores tend to report more intense altered states of consciousness. In the context of hypnosis, another phenomenon linked to phenomenological control, participants exposed to SLS typically did not report complex experiences unless primed to do so. However, the role of expectancy has not been specifically tested in relation to altered state of consciousness phenomena. Part 13. Neural mechanisms of stroboscopically induced visual hallucinations. Over the decades, several theories have been proposed regarding the neural mechanisms of these hallucinations. In the 1950s, Walter proposed that SLS induces visual hallucinations by disrupting how the brain supposedly scans across the visual field to construct visual experiences, a concept known as the traveling wave hypothesis. Costa theorized that these hallucinations might be entoptic phenomena originating in the retina. However, more recent research has highlighted the role of primary visual cortex and thalamocortical interactions in the generation of these hallucinations, with neural entrainment and higher-order brain areas also potentially contributing to these experiences. To date, the physiological mechanisms and neural correlates of these hallucinations remain debated, with 4 theoretical frameworks reviewed here as the most prominent explanations, followed by a discussion how such theories may overlap or be synthesized to form a more nuanced view of the neurobiological mechanisms underlying these hallucinations. Part 14. Neural Field Model Simulations. In the late 1970s, Ermentrout and Cowan formalized the idea that simple, geometric visual hallucinations originate in lower-order areas of the visual cortex through a theoretical model that demonstrated how patterns of activation in primary visual cortex could arise, which resemble certain Kluver form constants commonly reported during visual hallucinations. This model was later developed to incorporate additional anatomical features of the visual cortex, such as the diameter of cortical hypercolumns and their orientation selectivity. In 2011, Ruhl, Stoffregen, and Ermentrout applied these ideas specifically to stroboscopically induced hallucinations, demonstrating how a neural field simulation, when stimulated with a simulation of strobe light, could also produce geometric patterns which resemble some of Kluver's form constants. These models of simple visual hallucinations propose that dynamical interactions between local excitatory neural connections and long-range inhibitory connections lead to repeating Turing patterns across primary visual cortex. While these dynamics generate laterally symmetrical patterns of primary visual cortex cortical activity, these models suggest that these patterns are perceived as the radial tunnel, funnel, and spiral Kluver form constants due to the way that visual information undergoes a spatial transformation upon entering primary visual cortex. Neural field models of simple visual hallucinations therefore assume that the translationally symmetric patterns of activity in primary visual cortex are perceived as being concentrated and organized around the center of the visual field. However, this observation relies on the potentially oversimplified assumption that activity in primary visual cortex corresponds to phenomenal experiences, at least somewhat directly, which may not be the case. Furthermore, this model does not account for other commonly reported patterns with different geometric properties, such as the Kluver form, constant of checkerboards, lattices, or honeycombs, or more complex geometric formations reported such as kaleidoscopes or fractal-like forms. While in their original formulation of this model, Ermentrout and Cowan suggest that such laterally symmetric forms may only exist in the periphery of simple visual hallucinations. This claim is not supported by phenomenological data of the content of simple visual hallucinations. While the models are able to produce geometric imagery, which bears suggestive similarity to the kinds of geometric formations reported during SLS, the limited neural and phenomenological evidence that exists on this topic often diverges from their more specific predictions. Goulbenite aimed to measure the patterns of visual cortex activity during SLS using a mouse model, and found that standing wave patterns were generated exclusively within visual cortex. While the finding that geometric patterns form within visual cortices in response to SLS supports the notion that neural field models may explain certain aspects of hallucination content, the neural field models predict periodically repeating Turing patterns, not the standing wave patterns which best modeled Goulbenite's results. Furthermore, the neural field models predict that the spatial frequency of hallucinatory geometric forms will decrease as the stroboscopic frequency increases. The patterns measured in the mouse visual cortex exhibited the opposite relationship. Phenomenological data about visual hallucinations in humans may be more aligned with the results of Gulbinight's experiment, such as Smithy's observation that an increase in the spatial frequency of a hallucinatory pattern could be induced by suddenly increasing the frequency of the SLS. Additionally, Rule-Stoff-Regan and Ermentrout's neural field model further predicts two stable intervals of stroboscopic frequencies that would induce these hallucinations, yet generally only one is observed. While these models have provided initial insights into how these hallucinations may arise from cortical activity, other factors are likely involved in the formation of these experiences, such as the influence of neural processes in other areas of the brain and retina, as well as circuit-level neural interactions. Part 15. Neural entrainment. Neural entrainment in the context of SLS refers to the phase synchronization between a periodic stream of external flashes and neural oscillations, as measured using EEG. The most pronounced effect of SLS detected using EEG over visual areas of the brain is the steady-state visual evoked potential signal, which has been demonstrated to result from entrainment. The two main effects of neural entrainment due to SLS are an alteration in the phase of neural oscillations to match the phase of the SLS and an increase in the amplitude of the power spectra at the stimulation frequency. Despite neural entrainment being a prominent and well-researched neural effect of stroboscopic light, a mechanistic explanation which links neural entrainment to these hallucinations remains elusive. One approach to investigating the relationship between neural entrainment and these hallucinations involves experiments comparing the subjective effects of periodic and frequency-matched aperiodic SLS. These experiments have demonstrated that frequency-matched aperiodic stimulation substantially reduces reports of these hallucinations compared to periodic stimulation. However, these studies have so far not assessed the neural impact of aperiodic stimulation, making it impossible to definitively establish the relationship between neural entrainment and these hallucinations. While these results provide preliminary evidence suggesting that neural entrainment may contribute to the generation of these hallucinations, the direct relationship between neural entrainment and the experience of these hallucinations remains to be established. Part 16. Thalamocortical interactions. fMRI studies suggest that hyperconnectivity between thalamic nuclei and cortical regions associated with higher-order visual information processing plays a key role in the generation of these hallucinations. Specifically, experiments using frequency-matched periodic and aperiodic SLS in the alpha frequency range revealed that periodic stimulation increases both reports of these hallucinations and thalamocortical hyperconnectivity between ventral thalamic nuclei and higher-order visual cortices compared to aperiodic stimulation. The strength of the hyperconnectivity was found to correlate with the self-reported intensity of the stroboscopic subjective experience. Stroboscopic light stimulation may specifically target the ventral matrix of the thalamus, which has widespread projections to supragranular cortical layers and is thought to contribute to the regulation of conscious experience. Indeed, several theories of consciousness, such as dendritic information theory and the dynamic core theory, propose that thalamocortical interactions are crucial for generating the states and contents of conscious experience. This is likely due to the role of the thalamus in regulating cortical excitability and integrating information across cortical functional networks, enabling it to act as a central hub that orchestrates activity across the brain. In addition, the high spatial resolution of fMRI allows for the differentiation of specific areas along the cortical visual hierarchy that are activated by SLS. fMRI studies have shown that periodic SLS results in stronger activation within the lateral occipital regions, which are shape and orientation selective, and V3B, which is motion selective. Given that these hallucinations are primarily composed of moving shapes and patterns, it is likely that this stronger activation in shape and motion selective areas correlates with the experience of these hallucinations. To date, the relationship between these fMRI findings and neural entrainment remains unclear. While fMRI studies indicate clear increases in connectivity between lateral geniculate nucleus and primary visual cortex, these alterations in connectivity did not differ significantly between periodic and aperiodic SLS. In addition, changes in activation were not observed in early visual cortices, but rather in higher order regions. Given that the low spatial resolution of EEG does not provide detailed information about the precise neural regions in which entrainment occurs, improved source localization of the oscillatory activity associated with entrainment could offer valuable insights in this context. Furthermore, it is possible that the generation of these hallucinations is not solely driven by input from the lateral geniculate nucleus to the visual cortex, but also by the timing of thalamocortical feedback loops. For example, lateral geniculate nucleus projections to primary visual cortex may exhibit a frequency-dependent depression of excitatory postsynaptic potentials in response to SLS, depending on overall brain state, anesthetized or awake. Since higher-order thalamocortical projections have been shown to mediate the transition between anesthesia and wakefulness, visual cortical neurons may be influenced by functionally distinct thalamocortical pathways. In particular, the dynamics of higher-order projections may modulate the frequency dependence of geniculocortical response patterns. Therefore, the interaction between different thalamocortical feedback loops may collectively contribute to the phenomenal experiences associated with these hallucinations. Part 17. Predictive Processing Models. Over the past decades, predictive or Bayesian models of the brain have gained significant attention as a theoretical framework for explaining cortical information processing, including several formulations aimed at understanding the computational or dynamical principles underlying hallucinations. Central to these models is the idea that the brain's primary function involves continuously generating predictions about the causes of sensory events, with prediction errors, discrepancies between expected versus actual sensory input, driving learning and perception. The brain learns regularities about the world and uses this knowledge to internally generate predictions of the most probable upcoming sensory inputs, which are transmitted as top-down signals to lower-order cortical regions. The integration of these top-down priors with bottom-up sensory signals enables the brain to approximate Bayesian inference about the causes of afferent sensory input. Most interpretations of this process posit that perceptual content is given by the approximate posterior or best guess, which in normal circumstances, typical perception, can be informally described as a controlled hallucination. During typical perception, this process optimally combines prior knowledge with potentially uncertain and ambiguous sensory data to form useful, coherent percepts. However, various inductions of altered states of consciousness have been proposed to disrupt the balance between top-down and bottom-up signaling, leading to altered sensory processing, distorted perception, and the manifestation of hallucinations. Among several examples, researchers have developed computational models that propose how altered integration of top-down and bottom-up information could result in hallucinations. Although no specific formulation of the mechanisms of SLS within the predictive processing framework has been proposed, it is plausible that SLS could disrupt the computation of prediction errors. Adams, Bastos, and Friston formulated canonical predictive coding microcircuits that have been proposed to approximate Bayes' theorem within the functional architecture of a cortical column. Within this framework, the rhythmicity of the driving bottom-up SLS input may disrupt the natural balance of excitation and inhibition within a given neuronal population, potentially shifting the system to allow an excessive influence of prediction errors, which could result in hallucinatory percepts. Another possible mechanism is that the disturbance in visual information processing arises from inputs and interactions with non-sensory regions. During SLS, predictive processing could be disrupted by excessive thalamo-cortical input from higher-order thalamic nuclei to the cortical visual system. The strength and rhythmicity of these signals could interfere with the computation of prediction errors, potentially triggering the experience of these hallucinations. Indeed, the matrix thalamus is thought to play a central role in top-down processing. This speculative mechanistic hypothesis could be investigated through computational simulations of thalamo-cortical feedback loops in response to rhythmic input. Moreover, predictive processing models provide a powerful framework for explaining between subject differences in perceptual experiences in terms of variations in hierarchical processing. Predictive processing allows for individuals to differ in many aspects, for example, in the precision of prior beliefs, which would directly influence how sensory data is interpreted. In this context, prior beliefs can be strongly shaped by expectations related to the experimental environment. Stronger expectations may enhance the precision of these priors, which in turn could alter the perceptual outcome. More generally, when predictive models fail to reconcile incoming sensory data with prior expectations, alterations in hierarchical computations may lead to phenomena such as altered states of consciousness or hallucinations. In the context of these hallucinations, the strength and nature of these hallucinations may be influenced not only by the precision of priors, but also by an individual's level of phenomenological control. Individuals with higher phenomenological control may be more prone to consciously or unconsciously influencing the content and intensity of their hallucinations through more heavily weighted expectations. As such, expectancy and phenomenological control may be key factors in shaping the subjective effects of SLS, contributing to the diversity of experiences observed between individuals. Part 18. Towards a unified theory of stroboscopic light stimulation. The various perspectives described here regarding the neural consequences of SLS may coexist and interact with each other. For example, an electrophysiological study highlighted that phase locking entrainment occurs in neurons of the lateral geniculate nucleus, the first relay for visual inputs during SLS. This suggests that neural entrainment may be initiated in the thalamus before exerting downstream cortical effects. Given that the periodicity of SLS is crucial for many aspects of stroboscopically induced phenomenal and neural effects, it is possible that neural entrainment may serve as the driver for subsequent effects, including these hallucinations. Entrainment may trigger the perturbation of excitatory and inhibitory activity in early visual cortices, as described by the Ermentrout-Cowan model, leading to downstream activation of higher-order visual corticas via feed-forward pathways, as revealed by fMRI, enabling the conscious representation of the dynamic geometric forms to crystallize. Alpha band, 8 to 12 Hz, entrainment has been posited as a driver for these hallucinations, though this remains a topic of debate. Several studies have reported that these hallucinations tend to be more intense when SLS is delivered within the alpha band. However, these hallucinations can also be reliably induced by stimulation outside the alpha band. Qualitative differences in the hallucinatory experiences were reported when SLS is matched to intrinsic individual alpha peak, compared to stimulation 1 to 2 Hz above or below it. This is consistent with research highlighting the importance of the alpha band in the visual system. Nonetheless, since these hallucinations are reliably induced across a broader frequency range, approximately 5 to 50 Hz, it is unlikely that alpha band oscillations alone are the only contributing factor to the generation of these hallucinations. In addition, hyperconnectivity between ventral anterior thalamic nuclei and higher-order visual cortices may indicate a modulation of neuronal excitability in the visual cortex via matrix thalamic innervation. This could lower the perceptual threshold, increasing the likelihood of hallucinatory percepts. Future research could test this hypothesis using effective connectivity analysis to identify the directionality of connectivity changes between regions. Since the matrix thalamus also regulates arousal, its recruitment may also underlie the additional phenomenal effects of SLS, such as sleepiness and an altered sense of time perception, as well as other altered state of consciousness experiences. Finally, predictive processing may provide an encompassing framework within which these various neurophysiological processes can be understood as underpinning perceptual content during SLS, as well as accommodating individual differences in participant expectancies. A deeper synthesis of the perspectives described here into a comprehensive model of stroboscopically induced neural effects and their role in generating these hallucinations represents an important avenue for future research. Part 19. Future Outlook. Investigations into the subjective experiences induced by SLS face many open questions. To advance our understanding of this topic, future research should focus on improved characterization of the phenomenology of and neural mechanisms underlying these hallucinations. Developing validated phenomenological measures that can capture the full range of hallucinations is a crucial step in this process. Additionally, future work should aim to bridge the gap between empirical and theoretical phenomenological research by connecting more precise characterizations of these hallucinations with models able to simulate the wide range of visual features reported. This approach will help refine models of these hallucinations, which in turn can be used to elucidate their underlying neural origins, which can then be tested empirically. Clinical studies are also necessary to determine the efficacy and limitations of SLS for therapeutic applications. Research can also benefit from the insights gained from the use of SLS in recreational settings. Reported experiences with SLS vary widely, from overwhelmingly intense to minimal and boring. In recreational contexts, creatives working with SLS have access to a wide range of parameters such as brightness, frequency, duty cycle, wash light, music, and environment, which can be adjusted to create experiences of varying intensities. In laboratory experiments, experiential intensity has shown some variation, but stroboscopic frequency and luminance have been the only factors consistently linked to stronger subjective experiences. Further research should explore which combinations of stroboscopic parameters produce the most intense experiences and vivid visual hallucinations. Such studies could investigate the effects of adjusting the less explored aspects of the stroboscopic light or the use of more dynamic strobe sessions from recreational SLS, alongside investigations into the contribution of psychological factors such as expectancy and phenomenological control, which may play a significant role in shaping the subjective outcomes of SLS experiences. There is currently a renaissance of interest in SLS research. There is considerable untapped potential to explore. Stroboscopic and neuroimaging technologies are advancing, and applications and exhibitions that provide hallucination-inducing SLS are becoming increasingly successful and creatively developed. Simultaneously, multiple laboratories internationally are working with SLS to investigate the nature of visual hallucinations and consciousness more broadly. Stroboscopic light stimulation has already proven to be a valuable tool for exploring the phenomenology and neural mechanisms of visual hallucinations and potentially altered states of consciousness. At the same time, it remains a fascinating type of visual hallucination in its own right, with deep roots in both culture and experimental scientific research.